Earlier in the semester, we learned about a couple important proof strategies. In particular, we learned about backward planning and forward planning. We are now going to see what these proof strategies look like when applied to quantified sentences. Suppose that you want to prove a universally quantified sentence of the form for all x, ax. Now, backward planning suggests to identify the main connective of what you want to prove and to then use the corresponding introduction rule for proving this sentence. In this particular case, that means that if in line M you have the sentence that you want to prove for all x, ax, then you should try to prove the sentence AC, where C is a name, since that would then allow you to infer for all x, ax using universal introduction. Now, in order to be able to apply this proof strategy, you need to obey one important constraint. Specifically, the name C cannot appear in an undischarged assumption, and the variable x cannot appear in the line to which universal introduction is applied. So in this particular example, the variable x cannot appear in line m-1. Suppose that you want to prove an existentially quantified sentence of the form there is an x such that ax. Again, backward planning suggests to identify the main connective of what you want to prove and to then use the corresponding introduction rule. So applied to this particular example, that means that you should try to prove a sentence of the form AC, where C is a name in your language, since then existential introduction allows you to infer that there is an x such that ax. Now, to be able to apply this proof strategy, you also have to obey one important constraint. Specifically, the variable x cannot appear in the line to which existential introduction is applied. So in this particular example, the variable x cannot appear in the line m-1. Now, suppose you have among your premises a universally quantified sentence of the form for all x, ax. Forward planning suggests to identify the main connective of your premise or your premises and to use the corresponding elimination rule to derive further information from these premises. So applied to this particular example, that means that you should infer AC, where C is a name in your language, from your premise that all x are A. And you can then justify this inference using universal elimination applied to line 1. Now, this proof strategy has an important caveat. Namely, it can be difficult to know which name to substitute in for the variable x. So you kind of have to also look at what you want to prove in your proof to be able to know which name you should substitute for x. Now, suppose that among your premises you have an existentially quantified sentence of the form there is an x such that ax. Forward planning suggests to identify the main connective of your premise or your premises and to use the corresponding elimination rule to derive further information from this premise. So in the example that I have here on the screen, applying existential elimination would look like this. We would set up a subproof that starts with the assumption that AC and ends with the conclusion that B, where B is the overall conclusion that we want to draw in this proof. And the main thought is that if you are able to infer B from the assumption that AC, then you can infer B in line 5 and justify this inference using existential elimination applied to line 1 and the subproof from line 2 to the line B. Now, this strategy in a way mixes forward and backward planning. We first look at our premises, which in this case include an existentially quantified sentence, which suggests to us that we should use existential elimination. But then we also look at our conclusion, in this case B, in order to figure out what we want to prove using existential elimination. Now, just as with the other proof strategies, a successful application of this strategy also requires you to pay attention to a few important constraints. In particular, the name C cannot appear in an undischarged assumption before line 2, and it can also not appear in the sentence B that appears in line 4 and 5. So we have three main proof strategies: backward planning, forward planning, and indirect proof, as we have studied earlier in the semester. And just as we discussed before, you should apply these strategies in a specific order. In most cases, it makes most sense to start out by trying backward planning, since backward planning is a goal-oriented strategy. If backward planning doesn't work, then you should try out forward planning. Forward planning often has the caveat that it is not guaranteed that whatever you infer using forward planning actually brings you closer to the conclusion that you want to derive. And then in a third step, if forward planning also doesn't work, then you should try indirect proof. So first try backward planning, then try forward planning, and if all else fails, try indirect proof. So here's one proof intended to illustrate the use of our different proof strategies. What we want to prove is the sentence for all x, if ax, then b. And we have one premise, which is the conditional that if there's an x such that ax, then b. Now let's start by trying out backward planning. Backward planning suggests to prove our conclusion using universal introduction. In order to be able to derive this conclusion using universal introduction, I would need to have a sentence of the form if AC, then B in my proof. So that shifts our goal a little bit. Now I'm trying to prove that if AC, then B. And I'm going to use backward planning once again to continue to develop my proof. Backward planning suggests to prove this sentence using conditional introduction. Now, conditional introduction requires me to set up a subproof where this subproof starts by assuming the antecedent of the conditional that we want to prove and ends with the consequent of the conditional that we want to prove. Okay, so that's the state of the art right now. We have a subproof that starts with the assumption that AC and ends with B. How can we derive B? Well, now I'm going to shift my strategy and do a little bit of forward planning. So we have the conditional if there's an x such that ax, then b as a premise in our proof. And I see that this consequent here, b, is exactly what we want to prove. So that gives me an idea. If we are able to prove that there is an x such that ax, then we can infer b using conditional elimination applied to line 1 and this line here. But now proving that there's an x such that ax, in fact, is easy. I can infer this using existential introduction applied to line 2. And now I can infer b using conditional elimination applied to lines 1 and 3. I can infer if AC then B using conditional introduction applied to the subproof from 2 to 4. And I can infer my conclusion that for all x, if AX then B, using universal introduction applied to line 5. So that's our proof showing that the sentence for all x, if AX then B, follows from the premise that if there's an x such that AX, then B.